Alright, in this lesson we will take a look at an introduction to graphing using calculus. And of course in algebra you learn how to graph a straight line. All you need is to plot 2 points. You learn how to graph typical functions like a quadratic, a U-shaped curve. You could maybe locate the vertex. But the moment you get beyond second degree, graphing using techniques of algebra become very tedious and not so convenient. So calculus will help us pinpoint some important characteristics of a function. For example, the maximums, the minimums, the inflection points, which we're going to learn about today. And then graphing the function will be easier. So let's first get some ideas about some terms that we're going to be using in this section. And then we will take a look at some examples. So for example, we're going to use the terminology concave up and concave down. So the question is, over which intervals is a given function concave up and over which intervals is it concave down? So let's take a look at the graph. So clearly over this region it's concave up, right? We usually give the regions over the x-axis. So that region would be like negative infinity to 0. This function is concave up. And where else is it concave up? Like from this point A roughly to the point B, it's concave up, right? So from A to B. And also from C and beyond, it's concave up. So C to infinity. So over these 3 intervals, this function is concave up. And where is this function concave down? So over this interval, it's concave down. So you would give the region in terms of the x values. So basically from 0 to A, it's concave down. And where else is it concave down? Also from B to C, right? So over the interval from B to C, this function is concave down. Now if I ask you, where did this function change its concavity? You could say at the point A, concavity changed. Basically right here, whatever the function f of x value is there. At the point where x equals b, concavity changed, and x equals c is another point where concavity changed. We call those points inflection points. So those are very important points along the graph, and calculus will help us locate them so that the graphing the function will be easier. But also note that over here, over 0, concavity changed. So first it was concave up, then after that 0 point it was concave down. So note that concavity also can change across a point of discontinuity. So it can change across inflection points. It can also change across a point of discontinuity. Here's a similar question. This time we want to indicate intervals where the function is increasing and where it is decreasing. And then a similar question, indicate where did the function change its direction from increasing to decreasing or vice versa. Let's first look for the increasing regions. So over this region the function is increasing, right? So increasing from 0 to A and also from B to C. That's about it, because when you go from left to right, the graph should be rising. Those are the intervals where the function is increasing. Over the remaining intervals, the function is decreasing. Like over here, you go from left to right, it's decreasing. Then over here, it's decreasing, and over the last interval is decreasing. So those intervals are negative infinity to 0. Again, we give them over the x-axis. From A to B, and also from C to infinity. The function is decreasing. Now, let's take a note about at which points or across which points the increasing, decreasing nature of the function changed. Well, it changed across the point x equals A, x equals B, x equals C. What kinds of points are these? If you say they're like maximums and minimums, you are correct. So these are called local or absolute extrema for the given graph. So it is important to locate those points first. as well as the inflection points as you're trying to graph a function, because they will tell you a lot about the graph. But also notice that it was decreasing up to here, and then it was increasing afterwards. So it changed the nature of its increasing, decreasing nature also across a point of discontinuity. And this point right here is a sharp point, so notice that it can change its nature across a sharp point. This point would be called a point where derivative is not defined. And the reason it's not defined is because, how do you define the tangent line there? Do you define it in this direction? Do you define it in that direction? So it becomes like discontinuous in terms of the tangent line. So basically, it will be important to locate, when we graph a function, points of discontinuity, points where derivative does not exist, points like that, and also points where you have maximums and minimums, in other words, where slopes are horizontal. We call those critical points. So it will be important to locate those points, because those points hold the key to where this function will be increasing or decreasing. Now let's take a look at this function for a moment. And let me shade it a little bit so you don't have to look at everything at once. So we have y equals f of x, increases up to a, decreases afterwards. So we can clearly say this function is increasing from negative infinity to a, correct? Basically over this region. And over the x that's from negative infinity to a, this function is increasing. And over the second interval from a to infinity, this function is decreasing. Now what can we say about the derivatives? So up to a, look at the slope of the tangent line. All of these lines have positive slopes, right? And the slopes are actually going towards zero, but the point I'm trying to make here is that when a function is rising, the tangent lines are always going to have positive slope. So that means that your derivative will be positive. And the same goes that way. If the derivative is positive, one can say that the function is increasing. Similarly, when the function is decreasing, take a look at the slopes of the tangent lines. They're all going to be negative slopes. So the derivative, which represents the slope of the tangent line, right, will be negative. And the same can be said backwards. So when the first derivative is negative, the function will be decreasing. So in a few moments, I'm going to review those, because these ideas are going to help us put together a plan of action when it comes to graphing polynomials and other sorts of functions. Now, about concavity. The first one we see here, this graph, is it concave up or concave down? It's concave up, right? As you go from left to right, it's bending upwards. That's concave up. And also for a concave up function, basically tangent lines lie below the function. Now, what can you tell me about the slope of the tangent lines in a concave up graph? Now, this is also concave up, right? So it's not always has to be positive slope or negative slope. It can vary. It doesn't always have to be positive. It doesn't always have to be negative. But I want to point out to you here that slopes are getting steeper in a concave up graph. Like here, maybe the slope is 0.5. Maybe here the slope is like 1. Maybe here the slope of the tangent line is 2. So the slopes are increasing. So the function is, in this particular case, not only is increasing, but the rate of increase is increasing as well. So because slope was first 0.5, then 1, then 2. So that's the characteristic of a concave up function. So it's concave up, slopes are increasing. And remember, slopes is another word for that is f prime. So that means f prime is increasing. And here's the tricky part. This is a little bit hard to follow the following argument, but pay really close attention if you can. If something is increasing, let's review what we did earlier. Something is increasing, like here, f was increasing. Then what happened to its derivative? Its derivative was positive, right? Well, in this situation, the slopes are increasing, f prime is increasing. So if a quantity is increasing, then its derivative, so f prime prime, should be greater than 0, based on what we learned up there. So f prime prime happens to be f double prime. So here's the conclusion. If a graph is concave up, we expect the second derivative to be positive. And you can do a similar argument with concave down, and you're going to see that if something is concave down, slopes are decreasing. That means f prime is decreasing, and a quantity decreasing means its derivative is less than 0. So f double prime is less than 0. So now let me show you how we can put all of these ideas that we've discussed together into a plan of action, and you should have this handout in your on the website. Okay, so let's take a look. Okay, so here's going to be the steps that we follow to graph a function. First, we're going to want to find the relative max and min. That will also help us to find intervals of increase and decrease. To locate the relative maximums and minimums, we're going to find all points where the derivative is 0. Remember, those are the points where you could have maximums and minimums, soft peaks or valleys. Also, we need to find where f prime is undefined. Those are the points where you could have sharp corners. These points are called critical points. They are also candidates to be relative max or min. Then we will place the critical points on the number line, and we will select test values from each of the intervals determined. And we'll determine the sign of f prime. So we're going to say that this point was a critical point, this point was a critical point. So we're going to try to find, is f prime positive, is f prime negative over these intervals. I'll show you a way to do that. If f prime is negative, that means the graph is decreasing. Positive means the graph is rising. Negative means the graph is decreasing again. So already you would have a lot of information. Like here, you have a minimum because it's decreasing and then increasing. Here you would have a maximum because it's rising and then falling. So over here, again, it repeats the points from earlier discussion. That if f prime is positive, the graph should be rising. Negative, it should f prime negative, the graph should be falling. Also, let's take a look at the second derivative analysis, and then we'll do an example. Okay, to find inflection points and intervals of concave up and down, we will first look at the points where the second derivative is 0 and where second derivative is undefined. These are going to give us the candidates for inflection points. And remember, concavity changes across inflection points. And once again, we'll follow something very similar to the previous steps. We're going to put those points found on the number line, let's say 2 and 5. And let's say we have something positive. So we're going to check the sign of f double prime, because f double prime, second derivative of a function, tells you about concavity. If second derivative is negative, as it says down here, then you expect the function to be concave down. If second derivative is positive, you expect the function to be concave up, and so forth. So we're going to determine intervals of concavity based upon the second derivative. And to finish the graph, we may graph some of the y-coordinates of the important points found in steps 1 and 2. We're going to use the f prime chart and f double prime chart to get our directions, rising, falling, concavity kind of information, all going on the final graph. Okay, let's take a look at an example.